Okay, we're ready. Great, so it looks like we're right at 5 p.m. 5:01 p.m. we'll get started. I'm Dave Winters, the big data architect within the data science and engineering team at GoPro. A little bit of brief background on myself. I've spent, I always feel old when I say this, over 2 decades building backend systems in Silicon Valley, Bay Area. Everything from e-commerce backends to search relevance and ranking engines to corporate data warehouses. And the challenges we always had was always ingesting data faster, turning it around so that we could then store it in a format that our data analysts could quickly access the data. So that's what we're going to talk about today is basically the data platform that we built at GoPro. We're going to give you kind of an evolutionary story of basically 3 versions of the platform that we've built. And most importantly, we're going to talk about a feature which we call dynamic DDL, which is where we add structure to the data as it's being streamed in. So it's basically our 3.0 version of that. I have a co-speaker. Hao, would you like to introduce yourself?
Yeah, my name is Hao. I was a software engineer in big data area at GoPro right now. So before joining GoPro, I was working at the Alpine Data Lab, working on the machine learning platform. So today, David will talk about our high-level architecture of the dynamic DDL, and I will deep dive into our dynamic DDL with some code and some example. Yeah.
So, should have been on that. Should have shown off our great mugs there. So here's what we're going to cover today. I'm going to first give you just a little bit of background of basically the type of data we're dealing with at GoPro. Then I'm going to actually lead you through the architecture. And like I said, it's going to be kind of a story here of how we went through about 3 different versions of the architecture. And then Hal's going to go deep actually into some code, so it's going to be very hands-on, and talk about specifically how we do our dynamic DDL. So let's go ahead and get started here. So when we got to GoPro, basically, or when I did, basically, well, let me start with this. GoPro's been around about 14 years, plus or minus a year or so. And it started really with that guy right there, Nick Woodman, a surfer who wanted to capture basically life's moments on like a surfboard. He literally took a DSLR camera, shoved it in a Ziploc bag, and went surfing in Mexico with some friends. Just kind of went crazy with the idea of friends and family. They started to come up with prototypes, and they built the first GoPro Hero camera that way. After that, we actually started the GoPro Sponsored Athlete Program, which is hundreds of athletes across a wide field of sports, a lot of extreme sports, you know, kayakers and skydivers and stuff and doing crazy things. And then, of course, even into mainstream sports like tennis players, professional golfers, football players. They take our cameras, beat the heck out of them, and then come back and say, hey, this is what worked, what didn't work. That worked great when you just had one camera, worked for about $1 billion of revenue or so. But today, we have many versions of cameras. We have drones. We have all kinds of accessories. And it's also sometimes a little-known fact that people kind of miss is we actually have we're a big software shop. So we have a lot of software. Software that our end users use, our consumers use. So mobile application software that you can edit your videos, you can share them, same thing on the desktop. And so we realized at that point that if we were going to basically be able to continue to develop all these products and actually get feedback from our end users, we just can't just hand out cameras all the time, which we still do. We actually need to get data from everybody. And so that's where the idea for the GoPro Data Analytics platform was born. And the idea was to get anonymized logs, analytics logs from our devices and our software, understand how our end users were using the products, and what features they were using, what features they weren't using, and so we could improve them. So this is basically kind of a cartoon, kind of picture here of what we wanted to build and what we have today in production, running on about the 3rd version of it. But basically, the lower left-hand corner, you'll see all of the GoPro devices, cameras, drones, you name it, accessories that are smart and have microprocessors, anything that can send us a log, essentially. And then you'll also see at the very bottom there are the GoPro apps. And we also have a cloud, so the GoPro Plus Cloud, which is, again, another easy way where, especially our GoPro Hero 5 cameras, can automatically upload all of the videos and picture content automatically to our cloud and then allow you to very quickly edit and share them. And so all of these systems are instrumented. They all stream to us. That's our preferred way to get the logs, is to get them as soon as possible, and so to stream them. But then, of course, at the top there, you've got all of your traditional third-party sources of data, too, the e-commerce websites and systems. You've got all of the email campaigns. You've got the social media, OTT, which for those that don't follow that, that stands for over the top. It's essentially all the apps that run on set-top boxes and your Roku devices and your PS4s, those sorts of things. There's GoPro apps for those too. And then there's the classic back office stuff, the ERP systems, the NetSuites, the CRM systems, the Salesforces, and so forth. And we don't control that data because those are external third parties. We don't control the format or the schedule, or as we call it, the cadence of that data. But we do bring it all into one platform, link it all together, and that allows us to do the product insights, the classic insights are through visualizations such as Tableau and Plotly and so forth. And then we also take our data and it goes full circle here. So the data doesn't just come in, we also push it out to CRM, spam cannons, email campaigns, mobile device notifications, those sorts of things. So along the way, there's definitely a lot of challenges, and I touched on a few of those already, but you've got a variety of data here. You're dealing with hardware and software products, so you have to work with firmware teams that builds the software that runs on our devices. You have to work with the hardware teams also. You're dealing, again, like I said, with the external data sources, which we have very little control over the schedule of that data or the format of the data. We have a variety of data ingestion mechanisms. It is a Lambda architecture, which means we do both streaming and batch. Generally speaking, the streaming is internal applications and products, and the external is usually batch unless they support streaming. You have complex transformations because our cameras and our drones, which are very sophisticated hardware and software, they run a variant of Linux, they still have limited resources, both storage and compute. And so that means we get proprietary packed binary formatted logs, which makes it really fun when we're doing processing on them. And then, of course, you have every acronym under the sky, JSON, XML, CSV, you name it, for the other data formats. At the end of the day, we need seamless data integrations. We need to be able to link all the data. The data is really not very much of use if we cannot join the data together. So sometimes there's natural keys that can be used. Sometimes we have to insert artificial keys in between them so that we can link them. And then we also have to deal with the fact that all this data that we're getting, it's mostly event-based data. So it's when an event occurs. And a lot of times analysts want state. They don't want to just know that these various events occurred. They want to know what is the state of the camera at this time and those sorts of things. So we have to deal with building structures to reflect both event and state. And it's actually the last bullet here, but honestly it should be the top bullet, is privacy. It's one of those things, especially at GoPro, where from the very beginning PII was at the top of the mind. And so it's something, in fact, we'll talk a little bit about it in some later slides, how we handle that. But it's something that we take advantage or take very seriously right away. So with that, I'm going to go get more technical here. We're going to go into some architecture. So this is basically what which I colloquially refer to as our old file-based pipeline architecture. This is technically our 2.0 version of the GoPro data platform. The first thing to see is that you'll see in the upper left-hand corner is a real-time cluster. That's essentially how we're streaming in the data. You'll also see there's an ETL cluster, which is kind of like what it says in the middle there. That's primarily where you're doing your aggregations and your pre-joining. And then finally, you'll see there's a secure data mart on the right, and its job is purely just to execute SQL queries, lift the data basically into memory, do some basic transformations, and get it to the end user application. Now, on our 1.0 version of our data platform, essentially what we did was those three workloads, essentially the ingestion, the ETL, and then the delivery of the data were all in one big cluster. It was your classic data lake. It was reasonably structured, but the problem was the workloads were competing against each other. And the classic use case was this. Analyst comes in, writes a big gnarly query, maybe even a poorly written query, and it would bring the whole cluster to its knees, maxing out the I/O, and then your data ingestion starts to fail. So that was one of the first things we did with the 2.0 architecture or data platform, was to physically separate those three workloads. We do run everything in AWS, so that made it a lot easier. Well, I'm going to go just a little bit deeper down to each one of these clusters. So the real-time cluster is, as I said, that's where all of our streaming data comes in. You can see the upper left-hand corner, you see cameras and drones and the GoPro apps there. So those actually all stream in the data. It's generally mostly a mixture of JSON with or without compression. There also is the proprietary binary formats that we get from the drones and the cameras, which are packed pretty tight. Basically, what it looks like is you have a RESTful service. We happen to use Apache Tomcat for our pool of servers with some custom servlets. It's elastically scalable. It grabs the logs, does some basic authentication, and basically starts to stick those logs into Kafka as quick as it can. Then we go through a series of Spark streaming jobs, which basically is pulling logs out of Kafka, doing some processing, sticking them back into Kafka, and so forth, until finally it gets written into HDFS. We also do use HBase there. That's where we do the transformation from the event-based data and then into the state-based data. I will go deeper into the real-time cluster, and actually all these clusters in some future slides, but just to give you a quick overview. The ETL cluster, as you can see, we've gone from basically a mixture of some JSON and all sorts of different formats, and also in the proprietary binary formats, to the output of the real-time cluster is a nicely flattened out JSON format that's normalized. And so that all gets distributed copy over to the ETL cluster, anywhere from once every 30 minutes to once every 12 hours, just depending on the data source. The batch on the lower left-hand corner there, we do have a batch interface. That's mostly third-party software, third-party services, I should say. Basically, the batch framework is a custom Java framework that we wrote that can pull data down from a REST API, FTP downloads, S3. It's all configuration-based. So if there's any code that needs to be written, it's a very small amount usually. And then same thing, there's scheduled downloads. That can go anywhere from once an hour to once a day, just depending on how often we get data from that third-party data source. Everything meets up in the ETL cluster. That's where we pull out, originally it was all Hive with the MapReduce execution engine. Later on, a lot of those were being rewritten into Spark, obviously just to be faster, but essentially we do 4 things there. We convert everything from the flattened normalized JSON format into a columnar format, Parquet with gzip. We do pre-joining of tables to, again, make it so that our queries run faster for our analysts later on. We do pre-aggregation for the same reasons. And then we add the structure to the data. And what I mean by that is that's where we actually write to the Hive metastore and add new columns and define what the structure of the data is. We've always referred to our system as a data platform precisely for that reason, and not a data lake, because we've always added structure to the actual data. We've always had the Hive metastore, which is essentially our data dictionary for our data. We also use Airflow there, which is just for the scheduling of all those jobs. After that, basically everything is ready to go for querying. We've optimized it, highly compressed, especially since we have nice wide tables, which does mean you have a lot of repeating values. The compression ratios are excellent using gzip with Parquet that way. And so then we do another distributed copy, and again, it depends on the data source. It can be once an hour. It can be upwards of once every 24 hours, depending on the data source. It gets copied over to the secure data mart. At this point, we do kind of shift gears a little bit. We don't want to use MapReduce, and so we actually use Impala there. Essentially has a superset of HQL, and so it makes it easy for a developer to do both ETL and to do some queries, but it's a lot faster because it's an in-memory execution engine. The S, of course, we call it SDM a lot of times, Secure Data Mart. The secure part is we use Sentry, which allows you to use Kerberos and LDAP to do the authentication and authorization to make sure that the right eyes are looking at the right data. And then the primary access protocol for our data is actually ODBC for the most part. A lot of Tableau. GoPro is definitely a big Tableau shop. Hue, if people want to just do interactive queries. A lot of Plotly these days, as folks have started to migrate more towards the Spark notebooks. And then just good old-fashioned Python, a little bit of R. A few data scientists use that also. So we're going to take just a little bit deeper dive here into each one of those clusters. So this is the streaming endpoint, the real-time cluster as I referred to in the previous slide. So you have the logs here on the left-hand side coming in. Of course, it's a mixture, as I said, of the proprietary binary formats from our devices. JSON, sometimes compressed, sometimes not. They're hitting an EOB. For those that are familiar with AWS, we're 100% AWS, and so it's just our load balancer. It really helps us out quite a bit since you can elastically scale up our Tomcat servers that sit behind it with some custom servlets. The custom servlet does the basic authentication, and then it immediately starts to shove logs into Kafka as fast as it can. Kafka, what we do here essentially is you have this cycle between Spark streaming jobs and Kafka, And so you have a series of Spark streaming jobs that do some processing. They're reusable components, so they'll stick the logs back into other topics, and then further Spark streaming jobs will pick those off. And we'll go into that little cycle a little bit deeper in the next slide. Ultimately, what happens is the data is double writes. This is where we write the event data into HDFS, and then we accumulate the state data into HBase. And then finally, the data gets copied over every 30 minutes to 12 hours to the ETL cluster. So let's take that deeper dive into that cycle you saw there between Kafka and the Spark streaming jobs. So it looks something like this. You got your Tomcat server sitting in behind the ELB there. They're shoving logs as fast as they can into a root Kafka topic. What we do, the first thing we do is we take care of PII. So we've sat down with our lawyers. We've spent a lot of time with them understanding the various geographical regions and countries and so forth, and the codes and the laws and so forth they have. And so that's where all of that PII logic is applied. Basically, the removal, the hashing, the encryption of all the PII data, depending on what the opt-in and opt-out are, and of course, the country codes. After we do that, we start to basically route the logs into different topics. They get routed based on data source, several different factors. But what happens is you have this kind of tree-like structure of reusable Spark streaming jobs that are reading from Kafka topics, doing processing, and then writing the processed messages into the next topics. The interesting set of jobs here, or one of the most interesting ones, is the last column of Spark icons there, right before the HDFS. Those Spark streaming jobs are where things slow down. So most of the jobs to the left are running about every 2 seconds or so, as far as where they create a batch of jobs and they process it. When you get to that last column of Spark streaming jobs before HDFS, that's where we essentially have an impedance mismatch. You go from Kafka, which loves those little 1K messages, nice and small. That's where all the benchmarks you see, like published by LinkedIn and Microsoft, where Kafka has these crazy throughput numbers. They're always dealing with small messages. But now we're dealing with HDFS, and of course HDFS wants big files. You're going to kill the name node if you have all these tiny little files. And so we slow things down here so that we can get more into the gigabyte size of files. So usually it depends on the data source, once every 5 minutes, once every 15 minutes. It could be just once a minute. But the logs are essentially what we call compacted. So we collect them up, and then when we have enough data, we write them as nice large files into HDFS. And then they're ready to go. They're ready to be copied over to the ETL cluster. So the ETL cluster, again, this little deeper dive here. This is where we're merging in data sources. We got the batch data coming in from the lower left-hand side, our custom batch induction framework. And it has the same thing. It has a nice flattened out, normalized JSON format that everything is converted to. So it could be JSON, it could be text, it could be CSV, XML. They all get converted. And then you get the real-time cluster coming in from the top. That's a nice normalized, flattened out JSON also. And then originally it was a lot of Hive with MapReduce. Later on, actually I should have a Spark icon there. Later on, those jobs are being migrated to Spark, specifically Spark SQL for exactly what you'd think it would be. It's just a lot faster. We do those 4 things, which is basically convert from the JSON into the Parquet format with gzip. We do the pre-joins, we do the pre-aggregations, and then we add the structure, which means we write to the Hive metastore the structure of the data at this point. Once that's finished, we also do take snapshots. We take snapshots of the state. Usually it depends on the data source. Again, it could be by hour, it could be by day. But those are all the various entities that we have. We snapshot those, and now you have both event data and state data residing within the SDM cluster, or excuse me, within the ETL cluster, and then it gets copied to the SDM, which is our secure data mart. Secure data mart's pretty simple. We talked about it already a little bit. Basically, you get your Parquet files, you get your Hive metastore. They're all partitioned Hive metastore tables. We use Apache Sentry, Kerberos, and LDAP to lock it down. And then for the most part, it's ODBC is how the data is being accessed. Tableau, Hue, Python, there are actually Spark notebooks also being used. So that was definitely a huge improvement over our 1.0 version of our platform. We did an isolation of the workloads, right? So we isolated the ingestion of data from ETL from actual delivery of the data. Fast ingestion can support streaming, can support batch interfaces both. Secure, because we use Apache Sentry, Kerberos, and LDAP. Fast delivery of the queries, as long as you have enough memory, that is, but fast delivery with Impala. And then the nice thing is loosely coupled clusters. So you can do some maintenance if you need to on, say, the ETL cluster. Real-time cluster continues to do the processing, and vice versa. And same thing with the secure data mart. Bad things are things we can improve on. Multiple copies of data, 3 different clusters, 3 copies of the data, technically 9 copies if you count the triple replication HDFS. Tightly coupled storage and compute. This is a very painful one, especially when the holidays roll around. Good thing for GoPro, a lot of people like to buy GoPros on the holidays, especially Christmas Day and stuff, and we have to have a ton more processing power. Well, guess what? You get add a bunch more nodes. Even if you don't need more storage, well, they're homogeneous nodes, so you add the storage along with it, and then vice versa. If you need more storage, you end up getting more compute sometimes when you don't need it. Lack of elasticity. It's not very easy to add nodes. You have to deal with HDFS. Under-replicated nodes takes days, sometimes weeks, or a week or so to work itself out. And then just the operational overhead of multiple clusters, 3 production clusters that you're dealing with constantly. So with that, we began working on and actually have running in production today in parallel to our 2.0 platform. We have our 3.0 platform, which we call the dynamic DDL architecture. So the first thing you'll notice, you'll see a lot of similarities to the previous architecture. You still see there's a real-time cluster in the upper left-hand corner. You still see there's an ETL cluster. It's ephemeral now. And then you see there's the data marts. And of course, it's data marts now. It used to be just one now. So let's just kind of go through this one by one. So the real-time cluster, one of the first things you'll notice is that now we're no longer writing out the JSON files to the local HDFS. We're actually writing Parquet and DDL, and we're writing it to a centralized storage system, essentially. We use Amazon S3. We add the structure to it at the same time, the DDL. We write that to a centralized Hive metastore, which is now shared between all clusters. Same thing for the batch induction framework, does the exact same thing with the dynamic DDL. No more going from JSON to Parquet. We just go straight to the Parquet and the DDL. Work our way up to the top there, the ephemeral ETL cluster. Well, as I was saying earlier, with our ETL jobs, sometimes you have an ETL job that runs every 30 minutes. Sometimes you have an ETL job that runs once every 24 hours. But we would always have to scale our ETL cluster to basically be large enough to handle that 24-hour job. And so we'd just be sitting there, a lot of these nodes underutilized, for, well, probably 16 to 18 to 20 hours a day. So now we've been able to split that up. It's actually, the picture's not totally accurate. There's actually multiple ETL clusters now, and they have different schedules. And again, we don't have to pay for those nodes when we're not using them, and it's also a lot easier to elastically scale it up or down. And then same thing for the data mart. You'll see on the right side there. It's no longer just one data mart. We can have more. We can elastically scale up the clusters. So we can just make the clusters themselves larger, because the clusters are purely compute. The storage is separated from the compute. Or we can just add additional clusters if we wish. And then we also added the ability to use Spark notebooks for all of that. So with that, I will hand you off to Hal, and Hal's going to go a bit deeper into our dynamic DDL and actually walk through some code and how we do that.
Yeah, thanks, David. So now I'm going to deep dive into our dynamic DDL. So before I go deep dive into that, I want to review our high-level architecture. So I want to give you a high picture of where this dynamic DDL happened. So it's happened after we get the data, we consume the data from Kafka. So we have different kinds of topics from Kafka. So as soon as we get each topics, we will ingest the data directly into, adding the structure directly into the data, or even alter the structure if the same topic already exists in our Hive metastore. Okay, so from this point of view, you probably wondered, okay, what is a dynamic DDL, and why do we need a dynamic DDL, and how we did this. So the definition of dynamic DDL is really simple. It's just adding the structure in the data on the fly without whenever the data provider are changing their data structure or not. So as David already mentioned that we are not provider of our data, so we don't have a control of our data structure. So sometimes our data provider are changing their data structure constantly. So without this dynamic DDL, what we have to do is we have to manually update our database, our structure of our schema of the data when the data provider are changing the incoming data. So we have a lot of aggregation cycle. Without this dynamic DL, if the incoming data structure changed, we have to manually update this aggregation cycle. So that usually takes some people maybe a day or two to update this cycle, then to deploy this again on the cluster. So we want to faster turnaround of the data ingestion. So we don't want to leave this tedious job for the people to do this kind of work. That's why we introduce this dynamic DDL. We want to add in the structure as soon as the incoming data, even their structure are changed. So how we did this? We using, to sum it up, we basically using Spark SQL and the DATAFRAME API. In the next slides, I'm going to show an example of how we, the comparison of the fixed schema and the dynamic DDL schema. So before we come up with the idea of dynamic DDL, we use the idea of fixed schema. So basically, no matter the incoming data changed, we use a fixed schema. And that actually solved the problem of data provider changing their data structure, because we always use a fixed schema. But that introduced another problem, that our data scientists and analytics have to write some big chunk of SQL to pivot the data. So in the next slide, you will have a good understanding what is the fixed schema and what is the dynamic DDL. So take a look at this example. So this is a really simple JSON format data. So it has several attributes like ID, first name, last name, and city and state. So what we use to do is we first flatten the data into four entries. So the reason is that this data has 4 attributes in their record. So we flatten the data into 4 entries. We use the fixed schema called record K and the record value to make the schema fixed. So if the data provider changes this data structure, they add a new attribute, they add a country attribute, we will have another entry for this flattened data. So after we flatten the data, we can create a table based on the schema. So this 1 entry data will become the 4 entry in the database. So like I already said, so this is solve the problem of incoming data changing structure, because we always use the fixed schema. If the incoming data ID a new attribute, we just add a new column, add a new row. But it introduced a problem for the analytics and data scientists. They always complain about, okay, why do we have to write this big chunk of SQL to pivot the table? Because they want to analyze only one event, so they have to pivot this table to something to the 1 entry of data. So after they write this big chunk of SQL, they can get the analyzed data. So they complain about this. They don't want to do this tedious job. I feel sorry about that. That's why we introduced the dynamic DDL. So instead of doing this all flattened data and writing this big chunk of SQL, we directly create a table based on the schema. So in the next slides, I'm going to show you some example of codes, how we did this, how we actually alter the schema of the existing table. So like I said, we use Spark SQL and the Spark DataFrame API. So first we need to do is add a partition column. So this has nothing to do with the dynamic DDL, but it's a good practice for preparing the data, because when your data keep growing, you always want to partition your data. So next, we manually created the table using the Spark SQL here. So we are not directly using the DataFrame API to create the table, because there is a bug in the Spark. So if you're using the DataFrame API to directly create the table, the final table structure, the schema will get out of sync with the have method star. So that's why we have to use the Spark SQL here to create a table first. Okay. So next, what we did is we found the new columns from the incoming data that not exist yet in the our destination table. So basically, I mean, before Spark 2.0, we use 1.6. We can use alter table syntax to alter our existing table. But after we upgrade to our Spark 2.x, basically this syntax is not working anymore. So I think they already have a Jira ticket to take care of that. They promise that this feature will support it in Spark 2.2 or 2.3, yeah. So in case of, but we already upgraded our Spark to 2.x. I don't know if you guys, which version you guys using for Spark, but if you have a similar problem, we have a 3 workaround to basically bypass this problem. So this is like a 3 temporary way to solve the problem. The first way is pretty obvious. You can launch a Hive server 2 service, then use the normal JDBC to alter your table. But that actually, you have to maintain a separate service. The second way is using some Spark internal API to directly connect to the Hive metastore, then update the metadata. So this needs you to familiar with their internal API. The third way is using you can like update the Spark source code. Because in there, if you take a look at their source code, you can find they comment out this syntax support. You can uncomment that and made some API change there, repackage your code. You will be able to support this feature. So for our scenario, we couldn't repackage our Spark because we depend on our vendor. What we did is we call some Spark internal API to update our metastore. So I'm not going deep into this. So if you guys have a similar problem, you can contact us after this meeting, after this talk. Okay, so next, this is really important actually for the dynamic DDL. So after we alter the table, we got all the new columns. We have to reorder the incoming data structure to match the destination table structure. So the reason we have to do this is because the Spark doesn't, when you call Spark to save it, to insert your data, it will use a position-based context to insert our data. Basically, your column name probably, I mean, even the same column name will probably not in the same position. So what you have to do, you have to project all columns from the table to reorder the incoming data to match the position to the destination table. Okay, so the last thing you have to do is just append the data into your destination table. So before you append your data, you probably want to, in our case, we have to use coalesce to control our partition. Basically, the partition determines how many Spark tasks you will have in your Spark job. So we have we have so many partitions, like about 50,000 partitions. So it comes up with a problem. It's too many open files problem. So we have to use coalesce here to manually control the partition to a lower number to control the Spark job tasks. Okay, so now we have our data prepared for the data analytics to use. Even the new columns come in, we can handle that as soon as we ingest the data. So in our case, we have some problem after we ingest our data. I want to give you guys some tuning tips for that. So what we used to do, we use the process data and process hour as our partition key. But after about several months, we found that the hour we are using is not the date we are using is not correct. We are using the PST time zone, but we should use the UTC time zone. So basically, we have to repartition our data based on the new process data and the new process hour. But the data already been processed for several months. How are you going to repartition that without shutting down the existing pipeline? You can. So there is some tuning tips here. So first, there's a code snip here. You add your new partition key here. Then you use coalesce to control the job tasks to be a lower, like to make it. It's not like the number here is you couldn't make it too small, because if you make it too small in each job task, you will have too much data. It's probably out of memory. Then you couldn't make it too large, because if your like a number of coalesce too large, it will probably have too many files open problem. So you have to really understand your data. Okay, so then you partition basically. If your data is really large, you can use filter to filter your data. Okay, this is all I have today, and David already introduced the high-level architecture. So now we have 5 minutes for the question. Okay. All right.
So how often does your data timing, how often does the format change?
Well, that's exactly the reason why we developed the dynamic DDL. It's constantly changing, and so what would happen is we get a data source set up, and there's, gosh, I don't know, there's many data sources. I have no idea how many there are at this point, but as soon as you get it set up, they'd want to change it. And so it could be one of many mobile application development teams. It could be the cloud team, and they have a dozen or so different data sources, but they're always adding them. And so we were spending so much time constantly basically changing code to support the change of the format that what we did was we decided we're going to let you, as the data provider, control the format. And so we do have a payload spec, and what they all have to do is they can just add as many attributes as they want, and then we just continually add on additional columns as they send them.
So does this support only addition, or does this also support like removal of columns?
That's a really good question. So that was definitely one of the first questions we had is, do we need to support removal? And so what we've done is basically you can support with the Hive Metastore definitely several thousand columns without a problem. And at this point, we're definitely nowhere near that. But it is something that we have thought about in the future, that we may need to support the deletion of them. But we have let all the providers, data providers, know that there is going to be a limitation. You might not be near it today, but you'd be surprised at how quickly you can get there, especially when you're adding sometimes 100 attributes at a time. And so they need to track that one. But today we have not done that. When we get to that point, what we would do is, the nice thing is the Parquet file format does not have to match the Hive Metastore format, basically. And so you can actually just delete the columns from the Hive Metastore and never have to touch the Parquet files. So that's most likely what we'll do in the future. But yeah, we've never deleted a column yet.
Yeah, currently we didn't delete the structure, but we put a none there to it. Yeah.
Related to that, if there is any kind of data integrity issue,
Yeah.
the data you have already inserted before, how do you handle it?
Oh, well, what kind of data integrity issues are you referring to?
Okay, whether it's actually from the same sources, if your format have changed, whether it's like update.
Oh, I see.
Yeah,
Yeah.
like they renamed county to CNT1.
Yeah. Well,
New data.
absolutely. And so that is on them, and it has happened, and it does happen. You're absolutely right, because developer misspells it or something. They have it hard coded in their code, and then it's up to them to determine what is the correct spelling, essentially, for that column in this case. We have not to date gone back and updated any data. For the most part, we just roll forward, and that's kind of our policy, because we want them to really manage the structure of the data themselves. But we do use a Spark cloud-based service. We use Databricks today, and so now that we can do ephemeral clusters, we could reprocess data. We sometimes reprocess streaming data, but we could, if we wanted to, go back in time and reprocess those Parquet files. But I will admit, to date, we've really pushed back and we've never had to do it. So it's really up to the data providers to kind of govern themselves that way. But we also have them QA the data because they already have to QA their application anyways. And so we have them use our tools to actually QA their application. So that way, if there is like a misspelling somewhere, they usually catch it during the QA process and within the staging area and not in production.
How about the data type change?
So currently, everything are strings.
Yep.
And that's again one of the rules we gave to them. And the analysts are very proficient with Hive UDFs, and they know how to do the various casts into the type that they wanted to do that way. But they're responsible for basically ensuring it's in the right format. Yes.
Very like the DDL platform on that side.
Oh.
Very like the platform. I have a question about for the new columns that we're adding, kind of new structure which is coming in. If I have to use that as my new partition key, is there a provision I can add that first?
So today we control the partition keys as basically as we own the platform, and all of the partition keys for the most part are time-based. So they don't have any control over the partition keys today. It is something we've thought about, but we haven't had the need for it yet.
We have certain cases which I work on that big columns that's coming in.
Yeah, probably what we would. Yeah. Partition keys are tough because that one you really have to plan ahead of time. You can't just change the partition key on the fly. We have to kind of fall back to the one question about the data types and so forth. We have talked about coming up with naming conventions so that they could control the data type based on the column. We haven't really come up with a case for ourselves yet for the partition key. That's a really good one. I had to think about that a little bit because, like I said, you don't want to just switch the partition key in the middle.
Yeah, if you want to switch the partition key, you basically have to reprocess your data to use a new partition key.
I think the gentleman right here, I think, had a question in the green shirt.
Can you talk about the nested structure, how you handle nested structure?
So we flatten everything out. And so that's also, so everything becomes flattened out. Yeah.
What was the reason for Hive managed table instead of external?
Actually, I think we do now use external.
So
We've done both. We started off with managed,
yes,
and then we actually switched to external.
Some table we use managed table, some table we use external table. So for the external table, the good thing is we can delete the metadata for the table, but the table data will be there, so it will be easy for our migrating to our some different cloud services. So yeah, but even use the S3, you can still use the managed table for the S3 bucket. Yeah.
I think we have time for one last question.
Yeah.
Anyone? One last.
So when you say you're flattening the data out, I mean, like if it's a very deeply nested structure, the data tend to explode a lot.
It does, and and so that's where we work with like basically the data providers, especially if it's a GOPRO internal source, to let them know what's going to happen to their data, so that we can help plan basically the format of their logs or their messages, so that it's in a queryable format afterwards. Yeah. All right. Thank you very much.
Thank you, Ben.